Welcome back to our Chem 151 video series. In this video we'll do an example of how to draw a Lewis structure with noble gases. This problem gives us the formula XeOCl4. We'll begin by counting the electrons. We'll make a note of the number of each atom and the group each atom is in on the periodic table. We can begin by locating the atoms on the table. Xenon is located in the last column on the table, and our group number for that is 8A. Chlorine is located in the 7th column, labeled 7A, and oxygen located in the 6th column with the title of 6A. We'll record those in our table. Now we multiply that group number by the number of each atom. We have 1 xenon, 1 oxygen, and 4 chlorine. When we multiply straight across, we'll have 1 times 8 for xenon for a total of 8, 1 times 6 for oxygen for a total of 6, 4 times 7 giving us a total of 28 for the chlorine. Now we add all of the numbers together. 28 plus 6 plus 8 gives us a total of 42 electrons to place. Now we'll start with the xenon in the center, connected to 1 oxygen and 4 chlorines. We'll arrange the atoms around the xenon, and then we will draw 1 bond from each atom to the xenon. We've drawn a total of 5 bonds, and each bond contains 2 electrons. Since we're spending 2 electrons to make those bonds, we'll say -2 times 5 bonds gives -10 electrons. 42 subtract 10 gives us 32 electrons remaining. Now we'll begin placing some of our leftover electrons around the chlorines and the oxygen. We'll start with the oxygen because that's the most electronegative. We have 1 oxygen, and that oxygen can have 6 more electrons around it. We'll place those electrons now. We'll be using up 6 electrons to place those, and we'll say 32 minus 6. We'll get 26 electrons left over. Now we'll begin to place those electrons around the chlorine. We have 4 chlorines, and just like oxygen, we can place 6 electrons around each of them. We'll do this now. If we take 4 times -6, we'll get minus 24 electrons, leaving us with 2 left over. Those 2 final electrons will go on xenon. We'll place those underneath xenon now. Now we'll calculate the formal charge. We'll start with oxygen. Oxygen was in group 6, minus 1 bond, minus 6 electrons. If we do the math, we'll get -1. Then we'll do chlorine. Notice all 4 chlorines are identical, so we only have to run this calculation once. Chlorine was in group 7, minus 1 bond connected to each chlorine, minus 6 electrons around it, and 7 minus 1 minus 6 gives 0, meaning the chlorines are all neutral. Now we'll look at xenon. Xenon was in group 8. It is connected to 5 bonds as it stands, and has 2 electrons next to it, so we'll have 8 minus 5 minus 2, giving us +1. When we have a negative that's next to a positive, we take the electrons from the negative and move them into the middle. This will give us a double bond here, and we'll use up these 2 electrons. Moving those 2 electrons will bring oxygen's charge up by 1. It started at -1 and will go up to 0, meaning it is now neutral. Xenon, since it's gaining access to new electrons, will go down in charge by 1. Meaning it started at +1, but will go down 1 also to neutral. So the most stable structure is not the version that has the single bond between xenon and oxygen, but the version that has the double bond. We're going to base our answer for the molecular geometry on this new structure. Now that we have the correct structure, we'll find the molecular geometry based on what's going on around xenon. First, we need to find the domains. To find the number of domains, we look at the number of other atoms xenon is connected to. Never mind how they're connected, we just want to know how many there are, and how many pairs of electrons xenon has. So xenon is connected to 4 chlorines and an oxygen for a total of 5 other atoms. We don't care that oxygen's double bonded, we just want to know how many. Xenon also has a pair underneath it here, meaning that we have only one lone pair on the xenon. The lone pairs of the other atoms that are on the outside don't count toward this either. We add 5 plus 1 and get 6 domains. Therefore, to pick the right molecular geometry, we look for an entry that has 6 domains but only one lone pair. The second row of the information I've pasted is the row that has 6 domains. And then we look underneath the column to get the correct number of lone pair, and we see that our correct molecular structure is the one I'm circling now, called square pyramid. Which means the structure for the compound XeOCl4 is square pyramid. Thank you for watching. We'll see you again soon.